Thanks everybody for coming. Let's start with today's seminar. It is today my pleasure to introduce Roxana Rosca-Mead. Roxana did her PhD at the University of Cambridge under the supervision of Ulrich Sperhacker, and she's currently a postdoc at the TPI at the Federal University in Jena in Germany. So please, go ahead.
Thank you. So I'll be talking about what I've done starting my PhD and post-PhD on gravitational theory and in the context of core collapse. The results I'll present to you here is can be found also in two of the main papers we put out, sorry, one from 2020, and then a very recent one a few weeks ago that we just put up on the archive. Now, just a quick run through the overview. So I'll start by motivating what I'm doing and giving you an intro in the theoretical side. But then the talk will have two parts. First, numerical simulations that we've done and most of the results. And then based on those numerical simulations is our deductions and conclusions on if there's any observational potential in this modified gravity theory. Modified theory of gravity. Obviously, first question is why bother? I mean, GR has passed most of the tests we've thrown at it. It's flying colors, and even in the strong gravity regime now, we have excellent agreement since we started detecting gravitational waves. Now, despite all the success, there's still questions left unanswered, like the standard picture of the evolution and structure of the universe depends on types of matter that we have not yet detected, like dark energy, dark matter. And we generally expect GR to be the low energy limit of a more broader quantum theory. But starting from these points, many people have come up with a variety of theories to try and usually solve one or other issues that GR does not manage to explain. The theory I end up studying is this one there in this zoo. Just to give you an intro exactly at how it looks, for those of you who are new to modified gravity theories. So in the so-called Jordan frame, which is the physical frame, we have the Ricci scalar non-minimally coupled to a scalar field. So non-minimally coupled means the Ricci scalar gets multiplied with a function of that scalar, and then obviously you would put also a kinetic term for the scalar field and a potential term. And very importantly, we don't have the scalar field and the matter field directly mixed, though they influence each other through gravity. Now, leaving the action like this leads to quite more complicated forms of Einstein's equation. So you get particularly a couple more terms on the right-hand side of the Einstein equation, but more problematic is usually this F term of phi that appears here in the denominator. And you obviously get a wave equation for the scalar field. What we tend to do in this particular in these particular sort of theories is we perform a conformal transformation. So go from the physical metric to this scale metric, and also we redefine the scalar field from phi to var phi, which leads us to a way nicer, closer to GR action. So here the Ricci scalar that corresponds to this new metric doesn't couple directly with the scalar field. The only caveat here is that, as I said, matter fields don't mix directly with the scalar field. This is just a new redefinition of the theory, but this is what we normally consider the physical frame. So the matter fields couple directly with the physical metric. So G bar over F is the original metric. Now, this, in terms of equations, leads to tensorial form of Einstein's equation, closer to what we're used to, plus some more terms on the right-hand side. We have to give up in this case, though, the simplicity in the conservation of the energy momentum tensor, as we gain some terms on the right-hand side. And obviously, then we get a wave equation for varpha. So that's how it looks, the theory. Now, the question might be, out of that subset of what's been already suggested out there, why this particular theory? Well, scalars appear naturally in extra-dimensional theories, and they're prominent in cosmology. It is one of the few theories that's easy to work with, and it's been proven to be well posed. It shows interesting deviations from GR, such as spontaneous scalarization. A quick introduction. Spontaneous scalarization was first published on by Thibaut Damout and Esposito Farese in 1993. And what it means is, for stars of certain compactness, you start getting an extra family of solutions with a non-trivial scalar field, and they become energetically the favored star. So, for example, here's a plot mass on the vertical, radius on the horizontal for TOV-like stars in this theory. And what I do here is I vary just one parameter, and here the first frame here is just what you get normally from GR. And as I crank up one of the scalar-tensor theory parameters, you see that we're getting an extra branch of solutions. And what happens in spontaneous scalarization is that for if you have two models of similar varying mass, like a line here, where you'd also have a GR-like model, then the GR solution is unstable energetically, and the scalarized solutions out here are the stable ones. Okay, so that's one of the phenomena that appears. Another reason to look at scalar-tensor theory is because we could see some of the deviations from GR within the gravitational waves that are produced in this theory. In particular, actually a year before, in 92, they also published a longer and more general paper on multi-tensor scalar theories of gravity, and Damout and Esposito Farese also covered there the breathing mode, which is a nuclearization specific to this theory. We know that conservation of energy and momentum doesn't allow this mode in GR. We only get the plus and cross polarizations, but here we also now have this breathing mode, which is what I've been focusing on for this project. Now, last detail, why massive and not massless? Well, it's been shown, again, by Damout and Esposito Farese, that most deviations from GR can be expressed in a weak field in terms of log f being that function of phi that was multiplied with the Ricci scalar and its scalar derivatives at infinity. I put down here the actual expressions and connections if you're interested, but mainly because technically alpha 0 and beta 0 give you the leading terms in the Taylor expansion of log f. It is normal in the literature to use this expression for the coupling function, which is what we've done as well. So we tend to choose it to the -2 alpha 0 var phi. Var phi 0 is the value at spatial infinity, which we set to 0 throughout, and minus and then minus beta 0 var phi squared. Now, time delay measurements, solar system tests constrain alpha 0, and the most stringent constraint so far has been from the Cassini spacecraft measurements, which constrain alpha 0 to this value, and then binaries, usually observations from binaries constrain the beta 0 parameter And the most stringent constraint on it is whenever it needs to be bigger than minus 4.5. Probably to see it better, we have here from Freda and colleagues, they plotted alpha 0 versus beta 0. They drew the lines from different measurements, how it constrains the space of the parameter space. And they concluded that practically this shaded gray area is what's allowed in the massless scalar-tensor theory. This is a problem because to get spontaneous scalarization, beta 0 needs to be less than minus 4.35. It's dependent on the equation of state. So that means most of this parameter space doesn't really allow for spontaneous scalarization, which is one of the main interesting deviations that we could have looked at. So actually, this kind of killed interest a bit. So there was the odd paper then for 10 or more years, but not that much work done into it. And then in 2015, Petit in France suggested that, well, let's give the scalar field a mass. We make it practically decay exponentially with a radius as opposed to just as 1 over r as it does in the massless case. And this way, you screen its effects in the strong gravity and high density areas. If you screen those effects from like within a binary, they then calculated that this, if you make the mass large enough so that its Compton wavelength is less than the periapsis of the most stringent, the binary that gives the most stringent calculation, you get a lower limit for what the mass should be, which is 10 to minus 16 electron volts. Now, in practice, looking at TOV-like models or just using it in more dynamically situations like core collapse, when you use a massive scalar field, it actually kills a bit the scalarization as compared to the massless case. So on those grounds, you actually get an upper limit of 10 to the minus 9. And then by imposing that, neutron stars get scalarized, but not by dwarfs. They also get a very generous range for the beta 0 parameter, which leaves a lot to play with now. I would just say here minus 1,000 might be too much. I tried out of curiosity to do the TOV again for minus 100. I'm pretty sure I got to radii of 200, and I still did not get that bloody line to come back. It's still going and going. Okay, so this is why I looked at this theory. To give you an idea of the setup, so I do numerics, leave the big numerics lesson. Because we're looking at core collapse. To do this, we used a code built on top of the GR1D code developed by O'Connor and Ott, which has hybrid simulation shock capturing scheme, and it has now also the scalar-tensor theory implemented with the massive field. Now, core collapse, for those who don't know, is what the evolutionary endpoint of a star. So it happens to stars which are just burned out almost all their hydrogen. The core is mostly iron, and it has no more fuel to fight to oppose gravity, which is telling it to collapse. Thus, the star collapses until densities reach nuclear levels, where the repulsive nature of nuclear interactions then stiffens the equation of state and causes a bounce. This sends a shock outwards that slowly will start to will slow down because of neutrino emission and nuclide dissociation, and that's a more astrophysics area where it's still active research on how it's revived. Because if that shock manages to get to the surface of the star, you're going to get that beautiful supernova explosion, and you get a neutron star left behind. But if the explosion is weak or just never happens, then the proton neutron star that has been formed just accretes more and more mass until it goes over the maximum possible mass of the neutron star and then just flat. So that's just a crash course into core collapse. Now, because
we were interested in the breathing mode, which is we looked only at spherical symmetry. So our code was 1D. We modeled the baryon matter, we used a perfect fluid. For the equation of state, we used an analytic expression that tries to capture both the stiffening of the core when it reaches high density nuclear densities through the cold pressure part here, which is just the two piecewise polytropic function, and then also tries to capture the thermal effects after the shock goes through the material, and there's some non-adiabatic phenomena happening through the heat thermal here. As initial data, we used some realistic pre-supernova models from Lucy and Hale. So they involve non-rotating stars up to the point of core collapse using Newtonian dynamics. But they had a huge catalog, so we used a wide range of their stars from 12 to 75 solar masses and of 3 metallicities. Now, before I start talking about what happens in a massive case, I want to just do a recap of what happened in a massless case. So before I start my PhD, really did some work with Davide on this using GR1D. They looked at the core collapse of 2 particular progenitors, a lighter one of 12 solar masses that led to a neutron star, and then a heavier one of 40 solar masses that led here to a black hole. And they were looking at scalar-tensor theory parameters that were within the constraints. So you can see, try to remember sort of the value of the number. It just very suddenly, at the moment, the baryon density shoots up, so does the scalar field. You see here the scalarization happens very suddenly at this point. For the neutron star, you get amplitudes for this extraction radius of 20,000 kilometers of 40. Here, when you have a black hole of 300, here you see on both lines, it dropped very quickly. That's when the proto-neutron star happened, but then there was a very short intermediate proto-neutron star stage, because then a black hole formed very quickly and it started descalarizing. There's some limitations on the code because of the gauge it uses, so we can't actually evolve black holes. So what we do is we freeze the matter evolution. We let the scalar field dynamic still happen, just so that the scalar field travels to far too close to the extraction radii, and we can get most of the signal out. So that's why here it stopped at a non-zero value. So yeah, this is what happened in the massless case. Now, in the massive case, this is a selection of the waveforms we got. All the different lines show you deviations from the black one, for which there were different parameters I've pointed out here. We looked a lot for beta at around beta 0 is -20. And usually for this the scalar mass of 10 to the -14 electron volts. So as before, you had waveforms at actually lower extraction radii than this of 20 or order 100. Here you have order 10 to the 5, and it's also more wiggly. Now, I want to point out we get these much stronger waveforms, not because the mass does anything special. As I said earlier on, it kills scalarization technically. It's because now we could afford to go further into the scalar-tensor theory parameter space. So we didn't just limit ourselves to betas -4.5, for example. And that's why we got these very, very strong signals. A general characteristic of them, so they're very strong. Again, parameters less constrained. The signal is dispersed and it becomes more. I will show at one point plots of the scalar field at the center and then the full radial profile as it evolves in time. So at the center, the scalar field just looks like an inverted Heaviside function, which literally mirrors what the baryon density does at the center. But obviously, as I look at further and further out, it becomes more and more wiggly, which is something I'm going to cover in the gravitational wave section.
Sorry to interrupt. You said that is doesn't look like Coldplay.
Yeah. Oh, it's coded up to use the radial gauge performance license.
Okay.
But the moment collapses at zero, or to a threshold we set. Yeah. So I mean, it's also 1D and no neutrino, so we weren't going for precise numbers there, but we wanted to get an idea. Well, we would argue that the signals we got are probably an underestimate, because supposedly it doesn't fully descalarize. Yeah, these very strong signals we got, we call them hyperscalarization, which I'm going to play through for. And what's interesting is whatever progenitor, equation of state, alpha zero, beta zero parameter use, we can always, whatever alpha zero and scalar mass we use, we can always find a beta zero negative enough that we can always get these very strong waveforms. To try and give you a visual idea of that. So I've here we have the two plots. Top panel, you have on the x-axis the beta zero parameter, and on the y-axis the strength of the scalar field at the center, the maximum value it attains. And each line represents runs for different alpha zero values. You see, even if there's obviously it's proportional to alpha, the strength up to a point. The moment you hit beta around -9 here, they all jump and attain the same sort of value in strength. Which using more runs than just this, we also try to create a heat map to see this better. So here underneath you have again the same scale for beta zero, and then alpha zero on the vertical. And you see here there's a clear sort of threshold with regards to beta zero, for which from which point you always get strong hyperscalarization. So this particular one, we always use a 12 solar mass progenitor and equation of state 3. I forgot to mention when I was on the equation of state slide that it was one of the ones we used. We looked at 3 in particular, based on the fact that one was very stiff, never gave you black holes even in GR, and the other ones were a bit softer and have a bit more interesting behavior. So this is just one of the softer ones. We repeated this. So if you want to see more, I had loads in my thesis, which is available. But we repeated this for, as I said, this is the EOSA, the stiffer equation of state. Then for S39, which means a 39 solar mass progenitor. And it's the same thing. The threshold is not exactly at the same place. So a stiffer equation of state would you need to go further into the beta zero to get this threshold, to get the hyperscalarization. Whereas also with a heavier progenitor, you can afford a lower value, less negative values of beta zero to get hyperscalarization. But you can always find this threshold and always get those strong waveforms. Now this is the scalar field, and at one point we noticed that
Sorry. The threshold is the
sort of separating line.
When does it happen? What determines that?
To keep well, we look
tachyonic distribution. Right? So
yes, it's a tachyonic distribution. But initially you have this is also a bit scalarized of order, but kind of order alpha scalar field. And here the moment this scalarization happens is it goes into values of -0.35, for example.
Yeah, sure, but what
I think it's still tachyonic.
Yeah, but so what were you talking about here? Let's say effective content waveform.
order field equals the size of the star. Because beta 0 determines the effective mass. Correct? Effective mass squared that becomes negative when beta 0 is open negative.
I think so. I don't think I compared those exactly.
Yeah, I think that's okay.
But I'll think something to look at. Yes. So that was the scalar field. But at one point we started looking also, because we started seeing repeating patterns on what happens to the baryon density in all these, particularly as we get these very strong scalar field values. So here I show you in the top plot, you have in time plotted the central baryon density for different runs. The black is GR, and then there's 3 different runs there for 3 different beta 0 values. And underneath it, you have the central scalar field plotted. And this is what I meant when I said it's literally mirroring sort of the behavior of the baryon density. So we showed that we noticed that particularly when you have very strong values of the scalar field, so although 0.11, it influences the behavior of the baryon density. What do I mean by that? So we noticed that if you use less negative beta 0 values, then you get radiation with an amplitude of alpha 0, like you got in the master's case when you were looking at within the constraints. And the baryon density behaves just like we would do in the GR. That's the perfect agreement. And here, the scalar field is non-trivial, but it's of order alpha, which in this case was 10 to the minus 4, so it's just dwarfed by the rest of the lines. Then we noticed if we pushed the beat, I would say this is we're looking at the case where in GR we get a neutron star, not a black hole. If we push then beta 0 to more negative values, like -9, so intermediate, we noticed that, okay, there was a very quick attempt to kind of go for the same sort of density as in the GR case. So this was 4 times 10 to the 14th GS. And then it jumped to a higher value. And then later on, if I let the run go even to an even higher value around here, like 1.5, and considerably more compact model. So I put some numbers in some cases. So you could easily in the GR and it's the single stage low compact neutron stars, we could get neutron stars of maximum compactness of 0.07. Then after one stage, it went up to 0.11, and then after an extra jump, it went up. The compactness went up to 0.15, and it's measured at around 40 in that case.
So this multi-stage does not occur in GR.
No.
It's really just a
no. And the closest thing you have is when you have a progenitor equation of, say, where it goes into a black hole. It has that intermediate proto-neutron star stage, but then goes into a black hole. You don't really have that when the end result is a neutron star.
And what drives it? So this multi-stage is always a 2-stage.
Oh, it can be 3. Actually, so what? Let me finish this, and I can point that out. So if you push beta 0 far enough, it will go straight into sort of this higher value. It seems to be usually around 1, between 1.5, 10 to the 15 CGS in one go. Yeah, if values in between, it's almost like this jump might happen earlier, but sometimes the jumps become smaller and smaller and more almost smoothly tends from this line to this line. So I tried to do a long runs where I vary very slowly the beta 0, and I tried to put a heat map here with the category for each run. Trying to run that again. So here it just still looks like GR, then beta is strong enough to start getting loads of runs. And then here there were very small stages. I think at those densities you don't see them very well, but if I look at the full profile, I could see a shock forming and going outwards again. Which is actually one example I have here. So before I turn any of them on, so this is the full profile for what's happening. On the left, you have the baryon density, the full radial profile, and on the right, the scalar field. So yeah, here, this is an example for when you got the front flow compactness neutron star. So the behavior of the baryon density is exactly what it does to GR. And here you have in this case, order 10 to the -3, 10 to the -4 scalar field. So the bottom one also started, always for that. But yeah, this collapsed, bounced, and then a shock went out. I go back now. Underneath here is the case where you use very, very negative beta zero values, and it goes straight into 10 to the 15 sort of densities. And here I just so you can see sort of the values here is a close up, but actually this would disappear very quickly. So otherwise, this is very similar to this. Just goes, bounces, and then the shock goes out. And yeah, I think there is an atmosphere on the coast, so I think it's still accreting by this point. That's why it's slightly still decreasing. This one seems to be becoming faster. And then this is the case for the multi-stage. So you'll see first going into a weakly state or into a neutron star, just like it will do in GR at similar densities. And here you'll see the scalar field, which would be, well, actually that order is quite big as it is. But then you'll see, I think 2 more stages. That was one bounce, and then one shot. Then there was another bounce here. You saw there wasn't much of a jump here, but a shock formed and went out. And then in this case, there will be another bounce, which, yeah, the shock is seen only at lower densities, because here it would probably have been too small. Right. So this is, so technically this and this are 2 new scenarios that you don't get in GR. Then if we look at the progenitor that gave you a black hole ring in GR, similar plot presentation. So black here is what you got in GR. This magenta is for less negative beta zero values. If I wouldn't have gone for probability 0 or even positive, for this particular combination, they would have coincided. Then I didn't do a close up here, but yeah, the blue shows you 2, I think potentially 3 stages here, like a very short one there, and then it goes again into a black hole. Green here went to a neutron star, and I think the reason it's so short is because I could not afterwards continue it without some noise. There's always the question on when I categorize this, did I leave it long enough to run, or does it actually never go into a black hole? So I wouldn't swear by necessarily some of the values there of when the multi-stage neutron star finishes and when the multi-stage black hole finishes and when the neutron star happens. And if you push beta 0 long badly enough into the negative zone, you get again that very straightforward single stage high compactness neutron star. And except for the first one, where you get again radiation of order alpha 0, all other 3 will give you strong radiation. And I think this video is a bit better. So here, like black hole formation was delayed. Here, this first stage seems to be shorter and shorter until at one point it goes straight into the higher densities. And I again propose the radial cross for the two new, the multi-stage black hole, well, and the two-stage black hole, which again is just similar to what you'd expect in GR. So now a bounce goes into progenitor star, you've got the shock going out, kind of start seeing slowing down, and it's a bit wild. But yeah, at this point it froze because because of the limitations, but this still went on. And then this one, I think there were 2 or 3 intermediate stages. We had a protoneutron star, that's quite a weak scalar field. But then we're going to have another stage. And yeah, at this point it collapsed into a black hole. Okay, and I tried to, well, for all the runs I've done, categorize them based on that classification, and then superpose the heat maps from before with heat maps that kind of have these categories. And yeah, as you can see, always when we have these hyperscalarized models, that those areas coincide with the areas where you get these new collapse atoms. Okay, so this was fun for me. Obviously, there might be the question is this useful, observable, and so on. So let's next we always try to focus on what would we actually see by the time any signal comes to us. So apart from the source, we can approximate the scalar dynamics of the scalar field with a flat space pi-Gordon wave equation. I'm pretty sure Uli at one point might have talked about this in either the black hole workshop or just in a seminar here. But I'll just give you a quick run through. Using a substitution, we actually can rewrite the wave equation as a 1D wave equation. What do we see in practice? So if you are 2 waveforms, we extracted the blue one at 5 times 10 to the 7 meters, and the red one, 1 light second length further. Notice the fact that, well, the red one is smaller in amplitude a bit, but also way more oscillatory than the blue one. If we look at their power spectrum here, we see that the modes less than omega star, which is the frequency, characteristic frequency given by the scalar field mass, all these modes seem to decay already, even for the blue, for the smaller extraction radii, and by the time the signal reaches the larger extraction radii, they're almost all completely gone. But the higher frequency power is completely, it's completely preserved. So, as I said, we noticed the low frequencies are suppressed. The signals spread out in time. The group velocity of different modes depends on that frequency. So higher frequencies arrive earlier, ergo the signals become more and more oscillatory. And we actually got an analytical solution in the frequency domain for these for this equation. Now, this is all neat, but if you propagate this on galactic distances, I'm not sure there's a computer that will calculate the inverse Fourier transformation for this. But fortunately, that's not so much a problem, because after it propagates, say 10 kiloparsecs, the signal will be very stretched out, very oscillatory, but the frequency will vary very little compared to the amplitude, which means mathematically we can apply the stationary phase approximation and actually get a solution in the time domain for the waveform. So we did just that. So what we got practically this formula for propagating the scalar field large distances. The information from the original signal which we got from the which comes from the star, is retained here in the amplitude. So here you have part of the power spectrum and then a bit in the phase here. And what's very interesting about this, these will look quasi-monochromatic. So the frequency of these signals here, omega, will vary very slowly in time, and will have a characteristic variation like an inverse chirp. We actually plotted this here, so you can get an idea. The only bad thing is most information about the scalar-tensor theory, like alpha 0, beta 0, the parameters is lost, except for the scalar field mass. If you remember, this is given by the scalar field mass. So if you were to observe this and then observe long enough to see a bit of variation in time, you could deduce at least the scalar field mass. But why we're excited about this is even after propagating for 10 kiloparsecs, we could get very large amplitudes. Like for example, for the waveforms earlier, for these ones. So we propagated that signal 10 kiloparsecs, and we obtain the black line here, which is just its amplitude, because if I plotted the whole signal, it would just be noise at this point. And you see, it stays at a trivial value for a long period of time. Now, what does this mean for observational purposes? It means we could detect then all these gravitational waves in three forms. Burst signals. This is for the case the mass is very small, so it will not stretch it out so much. The signal itself will be only 1 second. But we're going back to the original problem of, okay, for light masses like that, then the constraints from solar system tests and the binaries of neutron stars will kick in, and then you will just not get those strong waveforms, so you're not going to see anything anyway. So, what would the point be? The second category is more interesting. It's when you get continuous wave signals, because for heavier scalars, you get a stretched out signal that the dispersion turns it into a quasi-monochromatic signal. And there's already pipelines in place to try and capture these, because rotating neutron stars, continuously rotating neutron stars, also emit continuous waveforms. And we have the advantage of assuming, because all these signals are dispersed and stretched in time, we could supposedly look at a historical supernova. And well, we know it happens, and then maybe say, okay, let's just see if there's anything left, point the interferometers, or look at that part of the sky. And another way to see it is as a potential stochastic background. I mean, we have so many sources that emit these signals that spread out and last for a long time, and then would have a very characteristic low frequency cutoff, and it might just be in reach of the LIGO stochastic searches. Now, we tried to actually put some numbers to, or order of magnitude for potential for each of, for at least the last two categories. So for the continuous waves, as long as you still have modes with power that are that have frequencies above the scalar field mass frequency, you're gonna see something at one point. We try to see what would happen if, say, you have an event, a star collapses at, in this case, we went with, again, 10 kiloparsecs to have a number. And you were to observe it for around, say, 2 months. I think in that period of time, the frequency would not change much, so we assume that it's sort of constant. So, starting from those assumptions, taking into account the interferometer antenna pattern, because obviously for 2 months the Earth rotates, so we took an average value. We looked at the signal to noise ratios and practically plotted the spectral noise density against the equivalent quantity, which we call the S0, to see what would be the potential. So let's focus on the red line. So these represent for different frequencies what we might see if we were to start observing this signals from this event. Say first point is after a year it happened. The second one after 3 years. I have here all the numbers. Then 10, 30, 250. I went a bit crazy with 1,000 here. Yeah. So notice. So the as we go further in time, the frequency will be lower and lower, just according to the inverse Chern formula. But the signal would stay relevant for quite a long time, and even with the current capabilities of LIGO, we could some part of the parameter space it could be constrained from the lack of observation, and then with the future interferometers, we'd have chances to constrain even further. There's the waveform, the amplitude is proportional to alpha 0 squared. I'll go on practically these lines being almost equidistant. So when the future generation interferometers would help us to constrain even alpha 0 quite a lot and better than the solar system test in the master space. Right, so we've done this for quite a few of our runs. I just wanted to put here a sample of them. And then as I said in the recent paper we put out, we looked at the stochastic background. So we built waveforms for several equation of state alpha 0, beta 0, scalar mass combinations using the catalogs from Lucy and Hager. We tried to take into consideration some event rates in the local universe. We amended the wave propagation to take into consideration the expansion of the universe. That just gave like an extra term in the wave equation, together with an extra term multiplied to the scalar field mass. And then we just integrated over all the events. I want to focus here on the cases where practically, irrespective of the progenitor used and the metallicity, the power spectrum of the gravitational wave signal looks the same. So practically these three models here, it's not noticeable because they agree so well, particularly in the low frequencies, but here you have around 40, and so here there's like 40 waveforms superposed, and here like 30. So look, these signals are all the type that give you those very compact prompt collapse neutron stars and hyperscalarization. To give you, we try to also look in the paper in the case where we're near the threshold, but obviously the threshold is a bit different for each progenitor, so we need to have more runs to integrate properly and interpolate. So these sort of models, these cases would come with considerable error bars.
Sorry, Roxana, I have a question here. So, can you remind me again, what are you using for the amplitude of at late times? How exactly is the scalar amplitude varying in time at late times?
For the gravitational wave.
Yeah.
I think I have it here. Sorry.
Yeah, I think it's there. Yeah, I think, yeah. So it's that.
So
right?
sigma was the one from the substitution where it was R times bar phi. So technically, here. So at the detector, the signal looks sinusoidal. to A. And A is practically that sigma solution over the distance, because sigma is r times bar phi.
So it doesn't vary with time.
What do you mean time? Which time? The length of observation, or no, that's here. T. So the signal to noise ratio would be proportional to square root of t, and inverse proportional to d, the distance to the source.
No, but what I mean is, I'm an observer measuring the field.
Yeah.
Okay, as time goes by, what do I see for the amplitude? Yeah. No, I know that, but at what time is that amplitude 80 of r? Is that what I should be looking at?
Oh, no, A is the amplitude of sigma, and if you remember, sigma is r times bar phi.
Yeah, but for time, that's irrelevant. I'm not concerned with this. I'm concerned with time.
Well, yeah, but okay, it's that rescale with the distance practically. Does that make more sense?
Okay, does it vary? Can you go there? Where is the time dependence there? There is no time dependence. Okay, it's in omega, capital omega. I got it. Okay.
Yeah.
Yeah, I think there's a 2 pi factor wrong.
Okay. We tend to. Right. So what I wanted to say here is, because of the universality of the signal in these cases, we focus on them because we could just assume every source produces the same. So we only have to pay attention at the event rate, their position, and take into consideration the redshift, but not worry about the actual distribution afterwards of metallicity and mass stars in the universe relative to us. Okay. Yeah, so we use the event rate models. Mostly in all of them, most of the energy contributions will come from a small redshift, and we obtain practically this. So the for these three cases, so beta 0 is -20, and for equation of state 3 and 1, and then for the more stiffer one, we have to go to -30 to get a sort of universal behavior. This is the energy spectrum we get for the stochastic background created by them. There's more uncertainty arising from the event rate model than from the fact that we use like the average of each of these house spectrum to build them. But it does show, for example, the equation of state 3, it seems to peak at around 80 here, and it's just about within the bounds of advanced LIDAR, but definitely it's possible to constrain this if you were to wait for the next 10 years for the future interferometers to go online. Right, so I don't know my time.
If you want any questions, you should stop as soon as possible.
Okay. This is literally a repetition of what I've said. So let's jump to questions.
You have questions?
For the continuous waves, so did anyone look at known supernovas?
No, because, well, as I said, this is order of magnitude. It's a 1D code. I've actually just been excited to saw today a paper on someone doing with a more modern equation of state and 3D with neutrinos, and they get the same behavior. But I think I want to redo some of these calculations with that sort of code to have an actual number to then actually go and constrain.
Right.
I would say this kind of gives you an idea where to look, so you don't repeat this with a 3D code. I mean, the advantage of 1D code is you don't need that many cores. So we did around 4,000 runs to kind of sort of get the whole picture, but that's not doable for a proper 3D simulation.
The axial storm may not be spherical symmetry, but it may be asymmetry. Then a star may have rotation.
Yeah, it's possible. And this was kind of, we focused on the 1D case, and because the code we had to use at that point was 1D.
You only study scalarization.
Like,
that massive.
so this paper that I saw was actually not sure the rotating, but it was in axisymmetry, and seemed to have the same sort of behavior. But they only pointed out 3 simulations, so I can't conclude anything.
More questions? If I may, a quick one. So these type of simulations, like in terms of how long does, even if it's just 1D, how long does it take for them to run? Like an example.
Standard resolution I used was like 15,000 points, 4 seconds, 3 weeks. I wouldn't go beyond that because I think numerical noise accumulates by that point too much.
Okay.
I mean, I did one for 20 seconds just for the fun of it, but yeah, noise. Yeah, it was visible by that point by eye. And yeah, if you use a slightly lower resolution, like 10,000, it could easily be done in a week. And it depends impressively when you do it for that long on the cores and the computers and the processors.
Mm-hmm. Thank you. Any other questions?
So in the stochastic report, for the sensitivity numbers. So I think the sensitivity curve depends on the polarization, whether it's a scalar mode or
so yeah, I think yeah. So I know these ones for the future ones that are extrapolation, and these yeah, I know there's
something I don't remember.
I think those we took into consideration, if I remember correctly, and the shaded area is based on whether if you were to observe for 2 years.
Well, because yeah, my question is just the light figures. Normally at these curves that they refer only for plus and minus, plus and corresponding.
We did have Mihaly, one of my collaborators. He's the expert on this, and he took that into consideration.
Okay. Last chance for questions. Okay. If not, let's thank our speaker.
If you enjoyed the video, like and subscribe.